Definition and derivation. A Poisson random variable x counts how many times a certain event occurs in a fixed period of time or space when the events happen independently, and the average rate is constant. If the average number of events in the interval is lambda, the probability of observing exactly k events is p of x equals k equals e to the minus lambda times lambda to the k divided by k factorial, for k equals 0, 1, 2, and so on. Derivation informal. Start with a binomial model. Divide the interval into n tiny subintervals, each so small that at most one event can occur, probability p. Number of events is distributed as binomial of n and p, with mean n times p equals lambda. Let n go to infinity, p go to 0 while lambda equals n times p stays fixed. Using the limit as n approaches infinity of n, choose k times lambda over n to the k times 1 minus lambda over n to the n minus k equals e to the minus lambda times lambda to the k divided by k factorial. We obtain the Poisson probability mass function. Numerical illustration. Suppose a call center receives on average lambda equals 3 calls per hour. What is the chance of getting exactly 2 calls in the next hour? Probability of x equals 2 equals e to the minus 3 times 3 squared divided by 2 factorial equals 0.498 times 9 divided by 2 equals 0.2240. So about a 22.4% chance. Mean, variance, and fundamental properties. For a Poisson of lambda variable, mean expected value e of x equals lambda. Variance var of x equals lambda, the spread equals the mean. Standard deviation square root of lambda. Key properties. Additivity, if x follows a Poisson of lambda 1 and y follows a Poisson of lambda 2 are independent, then x plus y follows a Poisson of lambda 1 plus lambda 2. This is useful when several independent sources generate events. Stationary increments. The distribution of the number of events in any interval depends only on the length of the interval, not on where it starts. Rare event modeling. Poisson works well when events are rare, but the observation period is long. Example calculation. A manufacturing line experiences on average 5 defects per 100 meters of wire, lambda equals 5. For a 200-meter roll, the mean defects are lambda 200 equals 5 times 2 equals 10. Mean equals 10 defects. Variance equals 10, so standard deviation equals square root of 10, approximately 3.16. If we want the probability of having exactly 12 defects in that roll, p of x equals 12 equals e to the minus 10 times 10 to the 12 divided by 12 factorial equals 0.094, approximately 9.4%. Poisson process and inter-arrival times. A Poisson process is a counting process n of t greater than or equal to 0 that satisfies. N of 0 equals 0. Independent increments, counts in disjoint time intervals are independent. Stationary increments, n of t plus delta minus n of t is distributed as Poisson of lambda delta. From these properties, the time between consecutive events, the inter-arrival time, follows an exponential distribution with rate lambda. T is distributed as exponential of lambda. The density f sub t of t equals lambda e to the minus lambda t for t greater than or equal to 0. Thus the average waiting time is 1 divided by lambda. Sample problem. A server receives requests at an average rate of lambda equals 5 per hour. Find the probability that the next request arrives within the next 10 minutes, 1/6 hour. Inter-arrival time t is distributed as exponential of 5. The probability that t is less than or equal to 1/6 equals 1 minus e to the minus 5 times 1/6, which simplifies to 1 minus e to the minus 5/6, which equals 1 minus 0.434, giving 0.566. So there is a 56.6% chance of receiving a request within the next 10 minutes. Explanation: modeling rare engineering events, system failures. Engineers often treat failures of highly reliable components as rare events. If failures occur independently and at a constant average rate, a Poisson model is appropriate. Worked example. A satellite subsystem has a failure rate of 0.02 failures per 1,000 operating hours, lambda equals 0.02 for a 1,000-hour window. Over a mission lasting 2,000 hours, lambda equals 0.04, we ask. Probability of no failures. P of x equals 0 equals e to the minus 0.04 equals 0.9608. Probability of at most one failure. P of x less than or equal to 1 equals e to the minus 0.04 times open bracket 1 plus 0.04 close bracket equals 0.9608 times 1.04 equals 0.9993. Thus the mission is almost certain to finish with 0 or 1 failure. If we observe 3 failures in a similar 2,000-hour period, the likelihood of this outcome under the assumed rate is P of x equals 3 equals e to the minus 0.04 times 0.04 to the third power divided by 3 factorial equals 2.1 times 10 to the minus 5. Indicating the assumed rate may be too low and prompting a redesign. Superposition and thinning of independent Poisson processes. Superposition. Adding 2 independent Poisson streams gives another Poisson stream whose rate is the sum of the 2 rates. N of t equals n sub 1 of t plus n sub 2 of t, implies n of t follows a Poisson distribution with lambda 1 plus lambda 2. Thinning, if each event of a Poisson process with rate lambda is kept with probability p independently of other events, the kept events form a Poisson process with rate p times lambda. Exam type example. Machine A produces defects at 2 per hour, machine B at 3 per hour. Defects from both machines are inspected together. 1. Superposition. Total defect process rate lambda equals 2 plus 3 equals 5 defects per hour. 2. During inspection, only 30% of defects are classified as critical. The critical defect stream is a thinned version of the total stream. Lambda critical equals 0.3 times 5 equals 1.5 critical defects per hour. Hence, the number of critical defects in 2 hours follows a Poisson distribution with lambda equals 3. The probability of observing exactly 2 critical defects in 2 hours is P of x equals 2 equals e to the minus 3 times 3 squared divided by 2 factorial, which equals 0.2240. Explanation: binomial to Poisson approximation. When the number of trials n is large, the success probability p is small, and the product lambda equals np is moderate. The binomial of n, p distribution can be approximated by Poisson of lambda. Step-by-step computation. Suppose a large batch of 10,000 electronic chips has a tiny defect probability p equals 0.0002, 0.02%. We want the probability of finding exactly 2 defective chips. Exact binomial. P sub b of x equals 2 equals 10,000 choose 2 times p squared times open parenthesis 1 minus p close parenthesis to the 9,998. Computing directly is cumbersome. Poisson approximation. Compute lambda equals np equals 10,000 times 0.0002 equals 2. Use Poisson probability mass function. P sub p of x equals 2 equals e to the minus 2 times 2 squared divided by 2 factorial equals open parenthesis 0.1353 times 4 close parenthesis divided by 2 equals 0.2707. Check accuracy optional : exact binomial gives approximately 0.2704, a negligible difference. Thus the Poisson approximation simplifies calculations without sacrificing accuracy when the rare event conditions hold. Given observed counts x sub 1, x sub 2, x sub n assumed independent and identically distributed Poisson of lambda, the likelihood function is L of lambda equals the product from I equals 1 to n of e to the minus lambda times lambda raised to the xi divided by xi factorial, which simplifies to e to the minus n lambda times lambda raised to the sum of xi times the product of 1 over xi factorial. Taking logarithms, L of lambda equals negative n lambda plus the sum of xi from I equals 1 to n times natural log lambda plus constant. Derivative with respect to lambda and set to 0. Derivative of L with respect to lambda equals negative n plus the sum of xi divided by lambda equals 0, which gives lambda hat equals 1 over n times the sum of xi, so the maximum likelihood estimator equals the sample mean. Illustrative data set. Counts of breakdowns observed each month for 10 months are 3, 2, 4, 1, 0, 3, 2, 1, 3, 2. The sample sum is 21, and the sample size n equals 10. Lambda hat equals 21 divided by 10 equals 2.1 breakdowns per month. Using lambda hat equals 2.1, the probability of exactly 2 breakdowns next month is p of x equals 2 equals e to the minus 2.1 times 2.1 squared divided by 2 factorial, which evaluates to 0.261. These examples illustrate typical exam expectations. Identify the correct Poisson model, compute the appropriate lambda, and apply the PMF or cumulative probabilities. A traffic engineer observes on average 8 cars pass a narrow bridge each minute. Assuming a Poisson model, find the probability that in a 30-second interval more than 5 cars pass. Rate per second lambda subsec equals 8 divided by 60 equals 0.1333. For 30 seconds, lambda equals 0.1333 times 30 equals 4. Probability that x is greater than 5 equals 1 minus. The sum from k equals 0 to 5 of e to the minus 4 times 4 to the k divided by k factorial equals 1 minus 0.785 equals 0.215. 2 independent sensors record radiation hits at rates 1.5 and 2.5 per hour. What is the probability that exactly 4 hits are recorded in total during a 2-hour observation? Superposition rate lambda equals the sum of 1.5, and 2.5 times 2 equals 8. Probability that x equals 4 equals e to the minus 8 times 8 to the 4th, divided by 4 factorial equals 0.057. In a quality control test, the probability of a defect in a single item is 0.001. For a batch of 5,000 items, approximate the probability that at most 1 defect occurs. Lambda equals 5,000 times 0.001 equals 5. Probability that x is less than or equal to 1 equals e to the minus 5 times. The quantity 1 plus 5 equals 0.0406.